Now imagine you're climbing up a power transmission tower and you come across a string of insulators, porcelain discs hanging like a chain between the tower and the high voltage conductor. Ever wondered, why don't they just use one big insulator? Why a whole string of them? And more interestingly, do all these discs share the high voltage equally? Let's dive into this mystery and uncover what really goes on electrically across this string of suspension insulators. Trust me, it's way more intriguing than it looks. So, a string of suspension insulators is simply a number of porcelain discs connected in series using metallic links. In reality, each of these porcelain discs acts like a capacitor. Yes, a capacitor. Why? Because there's a porcelain core sandwiched between two metal fittings, forming what we call the self-capacitance or mutual capacitance of the disc, denoted as capital C. Now, if we consider only this self-capacitance, then things are straightforward. All discs would carry the same charging current, and hence the voltage would be evenly divided across all of them. If we had 3 discs, each would take V by 3 volts. Simple, right? But hold on. In real-life situations, there's a twist. We also have shunt capacitance. This is the capacitance between the metal parts of each disc and the grounded tower or earth, denoted by C1. This additional path changes the entire voltage distribution game. The presence of these shunt capacitances means the charging current through each disc won't be the same anymore. The disc closest to the line conductor now gets more current, and hence, more voltage. So in practice, the bottom disc, the one nearest to the conductor, is under maximum electrical stress. As we move upward towards the tower or cross-arm, the voltage across each disc decreases. That's why V3 is much greater than V2, which in turn is more than V1. And here's the big concern. Since that lowest disc is under the highest voltage stress, it's the most likely to get punctured first. That's dangerous because once one disc breaks down, it can lead to a cascade failure across the rest of the string. Now let me ask you, did you ever think all the discs carry equal voltage? If yes, you're not alone. Drop your thoughts in the comments. I'd love to see how many of you thought the same before. Also, if you haven't already watched our previous video on insulator types and their behavior, I highly recommend watching it before continuing. It will help you connect the dots. Alright, now that we understand the unequal voltage across the discs, let's define something very important: string efficiency. This is the ratio of the total voltage across the entire string to the number of discs multiplied by the voltage across the disc nearest to the conductor. So if V is the total voltage and V3 is the voltage across the disc closest to the conductor and N is the number of discs, then string efficiency equals V divided by N times V3. This efficiency tells us how evenly the voltage is spread across the discs. A 100% efficiency means perfect distribution. Each disc gets the same voltage. Sounds like a dream, right? But in practice, 100% efficiency is nearly impossible due to the shunt capacitances. Still, we try to get as close as possible. Let's now break this down mathematically, and I promise it won't be boring. Imagine we have 3 discs in the string. Each has self-capacitance C. The shunt capacitance, or C1, is K times C. That means C1 equals K multiplied by C. Let's denote the voltages across the top, middle, and bottom discs as V1, V2, and V3 respectively. Applying Kirchhoff's current law at the top junction A, we write, the current going into the node, which is V2 times omega C, is equal to the sum of V1 omega C and V1 omega Kc. Simplifying this, we get V2 equals V1 multiplied by 1 plus K. Let's call this equation 1. Now at node B, similarly, V3 omega C equals V2 omega C plus V1 plus V2 omega Kc. Solving this gives us V3 equals V2 plus K times V1 plus V2. Substituting V2 from equation 1, we get V3 equals K times V1 plus 1 plus K squared times V1. Finally, we get V3 equals V1 multiplied by 1 plus 3K plus K squared. That's our equation 2. Now total voltage V across the string becomes V1 plus V2 plus V3. Substituting all, we get V equals V1 times 3 plus 4K plus K squared. Or V equals V1 multiplied by 1 plus K times 3 plus K. That's equation 3. From all this, we get a golden set of ratios. V1 divided by 1 equals V2 divided by 1 plus K equals V3 divided by 1 plus 3K plus K squared equals V divided by 1 plus K times 3 plus K. This helps us calculate voltage distribution across each disc once we know the total voltage and the value of K. For example, If K is 0.2, then V2 becomes 1.2 V1 and V3 becomes 1.64 V1. That's a huge difference between top and bottom units, right? So here's another question for you. Do you think increasing the number of disks helps in reducing this inequality? Think about it and let me know in the comments. Now let's move on to how to improve this string efficiency. So we've seen that the bottom disk gets the worst of it. Let's explore what we can do to balance things out. First, we can use longer cross arms. Why does that help? Because it increases the distance between the disk fittings and the tower, reducing the shunt capacitance C1. That means lower value of K and hence better string efficiency. But longer arms mean higher cost and structural complications. In practice, reducing K to 0.1 is the best we can usually achieve using this method. Second, we have grading of insulators. Here, instead of using disks of equal size, we use disks with increasing capacitance from top to bottom. So the top disk has the lowest capacitance and the one near the conductor has the highest. Since voltage is inversely proportional to capacitance, this makes the distribution more uniform. But the downside? You'll need a variety of insulator sizes, which complicates manufacturing and inventory. Still, it gives good results. Finally, and most cleverly, we can use a guard ring. It's a metal ring attached to the conductor and surrounding the bottom disk. It adjusts the capacitance values in such a way that the shunt currents balance out the line currents, ensuring uniform current through each disk and hence uniform voltage distribution. Smart, right? Before we jump into the example, here are 3 golden rules to remember. 1. The disk nearest to the line conductor always has the highest voltage. 2. The total voltage across the string is simply the phase voltage, not the line voltage. And 3. Line voltage is root 3 times the voltage across the string. Say we have a 33 kV overhead line with 3 units in the string. Shunt capacitance is 11% of the self-capacitance. Let's find the voltage across each insulator and the string efficiency. Now, 33 kV is line voltage, so the phase voltage or voltage across the string is 33 divided by root 3, which is approximately 19.05 kV. Let's take V1 as the voltage across the top disk. From earlier derivation, V2 equals V1 multiplied by 1.11. V3 equals 1.342 times V1. Total voltage V equals V1 plus V2 plus V3. That's V1 plus 1.11 V1 plus 1.342 V1, which equals 3.452 V1. So 19.05 equals 3.452 V1. That gives us V1 equals 5.52 kV. V2 becomes 6.13 kV and V3 is 7.4 kV. Now for string efficiency. It's total voltage divided by 3 times voltage across bottom unit, which is 19.05 into 100 divided by 3 into 7.4. That comes out to around 85.8%. Not bad, but still room for improvement. So, do you think using a guard ring here could push the efficiency closer to 95%? Let me know what you think in the comments. I hope this breakdown helped you understand the beauty and complexity of suspension insulators. If you enjoyed this deep dive and want to see more examples like this, go ahead and hit the like button. And yes, don't forget to click on the thanks button if you found value in this content. It helps the channel a lot. If you want to support electrology even further, you can also hit the join button and become a channel member. See you in the next video. Until then, stay curious and keep exploring the world of electrical engineering with electrology.